Hello everyone, my name is Miti Mazmudar and I'm a PhD student in the CRISP lab at the University of Waterloo. Today I will be presenting our work, DHTPIR, which was done in collaboration with Stan Gertler and Ian Goldberg from the CRISP lab. Here we provide an interface to privately retrieve documents over distributed hash tables or DHTs. We have published a short paper in the WPAS workshop as a part of CCS 2021, and we also published an extended archive report. Protocol Labs has called for proposals on private retrieval of data, and Shannon, Rasul, and I have submitted an application, and at the end of this talk, I'll be discussing extending DHTPIR into IPFS through this proposal. I thank Will and Yanis for providing me with this opportunity to present DHTPIR. So everyone here knows that IPFS is a peer-to-peer application that is based on distributed hash tables or DHTs. The content that we store on IPFS is distributed across IPFS nodes. Information on how to get to a node that serves the content or the routing information is also distributed across nodes. In this diagram, we visualize the DHT virtual address space as a circle. So consider node P that wants to fetch a block acting as a client. We can see node P's routing table, and we can see that it has routes to nodes R, S, T, and X. The client P conducts a query for that block, which we will refer to as a content query. In the process, it may contact many other nodes, such as node R, and ask for the routing information to iteratively get closer to the nodes that store the block. Suppose that's node B. So the client may also conduct routing queries in order to respond to a content query. Whenever a client fetches a block from the DHT, intermediate nodes such as node R can learn that the client is looking up routes for a node with a given node identifier, or that it is looking for a block with a given content identifier, or CID. The server node such as node B learns that the client has asked for and retrieved a block with the CID. The client may have looked up sensitive content, so the client may not want the server node to know that it has looked up this block ID. The intermediate nodes also ought to not know what the client is looking up or which nodes the client is trying to contact. More people may be inclined to use IPFS to search for sensitive content when they are assured that the content of their queries is not known to other nodes. So conducting routing and content queries privately directly benefits client nodes. Additionally, more nodes may participate as server nodes if IPFS further minimizes information that they are exposed to. This is the notion of plausible deniability. Let's talk a bit more about that. So consider IPFS node operators who may store sensitive content and are in a censor's region of influence. So these node operators may be compelled by the censor to reveal what block identifiers were retrieved in a content query by a given user. For example, consider a censor who requires node operators to log content queries in plaintext form and forward them to the censor. A censor may consequently harm users who query for blocks corresponding to prohibited content. Suppose that a content query is constructed carefully such that a node operator cannot determine the content identifier or CID, and yet they can answer the content query successfully. Then the node operator can plausibly deny knowing what a given user asked for through that query. In turn, a censor can no longer learn which blocks were requested via the IPFS node operator. So providing plausible deniability over queried content can incentivize more users within a censor's region of influence to contribute their disk space and bandwidth to serve as IPFS nodes. IPFS has been used to evade censorship, and our work can benefit IPFS node operators in a censored regime. Right, so our work, DHTPIR, allows users to retrieve documents from the network without revealing what document was retrieved to the target node that stores the document, nor to any in-path nodes. We provide a complete algorithm for users to query privately for files, as well as an algorithm for publishers to store copies of the file in a way that supports private querying. Note that we do not provide anonymity to any node, that is, we do not protect the network identity of the client peer. The adversary can see that the client is communicating with a given set of nodes. Right. Our interface can be integrated within a distributed file system, such as IPFS. For this integration to work, the underlying DHT first needs to be strengthened with additional security and privacy building blocks, such as quorums and quorums-based secure routing. I'm going to start with the background for our work and proceed to the design of our protocols. I'll briefly go over the security guarantees and a performance analysis of our protocols. I'll then present our evaluation. To conclude this talk, I will outline directions for integrating our work into IPFS, which we will address through our proposal. So we show these various building blocks for our system here. We begin with a brief background on private information retrieval, or PIR, as it naturally provides the data minimization and privacy guarantees that we seek. We focus on IT-PIR schemes, which require quorums of server node operators. Quorum constructions have been separately proposed to harden DHTs. They've been used in robust routing, such as Young et al.'s robust communication protocols, to provide integrity of routing entries and prevent eclipse attacks. Backus et al.'s query privacy protocols extend RCP to additionally provide confidentiality over routing entries. In the setting of private information retrieval, we have one or more untrusted server applications that share a database. We can have multiple clients. Private information retrieval allows clients to query these databases while guaranteeing that the servers cannot learn which index of the database was accessed. PIR schemes are classified into one of two types, depending on their threat model: computational or information theoretic schemes. Computational PIR or CPIR schemes rely on the hardness of cryptographic problems. Information theoretic or IT-PIR schemes require two or more servers that host the same content. The threat model of IT-PIR schemes requires that all of these servers do not communicate or collude with each other. IT-PIR schemes are preferable to CPIR schemes in terms of performance. Specifically, they have a lower computational complexity. So here, 4 servers and a client node engage in a simple IT-PIR scheme. The client wants to retrieve an index at an item K from the server's shared database. It first constructs a non-private unit vector, IK, with a 1 at this index and 0 otherwise. The client generates 4 random index vectors, R sub I, such that by themselves they reveal nothing about the client's desired index, but when they are combined in some special way, so through the XOR operation here, the client gets back the unit vector. So the client sends 1 random index vector to each server. Each server uses its index vector to look up the database and returns with a PIR response. Here, the PIR response is simply the product of the PIR request vector with the database. In the reconstruction step, when the client puts all PIR responses together in the same special way, it will get back the desired item. Note that if all of the 4 servers shared their respective index vectors with each other, then by XORing the 4 index vectors together, they can tell what row the client looked up. So IT-PIR schemes make the assumption that the servers will not team up and collude with each other to learn what the client's request was. This is known as a non-collusion assumption. In this simple scheme, all 4 nodes need to be available online for the client to be able to reconstruct the desired row. In general, Byzantine-robust IT-PIR schemes only require a threshold of nodes to not collude with the others. Even if other nodes provide incorrect responses or fail, the client can reconstruct the desired row from just this threshold number of PIR responses. So going back to the DHT setting, suppose that we can trust a group of DHT nodes to not collude with each other. With this assumption, we can arrange for these nodes to share the same database and conduct Byzantine-robust IT-PIR to enable a client node to retrieve files privately. As it turns out, some security properties for DHTs, such as robust routing, require that most of a node's neighbors are not Byzantine nodes, that is, that they are honest nodes. Many constructions have been proposed to organize nodes in different DHTs into small groups, such that most nodes in each group are honest. So essentially, we have these threshold honest groups for some high threshold. Example quorum constructions include Escademlia, which is Baumgart and Mises' extension over Cademlia. My understanding is that there is work in progress to incorporate escademlia into libp2p. While developing our system, we had focused on Sen and Friedman's Commensal Cuckoo rule, or CCR, for quorum construction. So in this diagram, we can see that the CCR splits the DHT virtual address space into quorums. Here the quorums have 4 or 5 nodes each. And in this diagram, we have 9 Byzantine nodes and 47 honest nodes. So the global fraction of Byzantine nodes in the network is 0.16. Now, the CCR allocates a joining node, which may be honest or Byzantine, to a particular quorum in the DHT, such that no quorum has more than a certain local fraction of Byzantine nodes. So this local fraction may be much higher than the global fraction that I just mentioned, which was 0.16. So, for example, you can see that the maximum local fraction of bad nodes in any quorum is 2 by 5, or 40% for quorum 6. Now that we have these threshold honest quorums, let's look at how nodes in a quorum can communicate with each other. So instead of maintaining a routing entry for a peer with the given peer ID, each node maintains links to quorums of peers that span a small virtual address space. Right, so quorum 1 here can communicate directly with quorums 3, 7, 10, and 12. So for example, each node in quorum 1 maintains routing entries of network addresses for each node in quorum 7, as well as their public encryption keys. So suppose that node P in quorum 1 wanted to talk to quorum 6. The first step would be to look up its own routing table for the quorum that spans the closest address space to the target quorum. Here, that's quorum 7. So node P could ask a node in quorum 7 for its closest routing entry to the target quorum 6, and the contacted node responds back with the routing entry of quorum 6's nodes. But then maybe node P ends up contacting a bad node R in quorum 7, who responds back with a fake quorum of its bad buddies from quorums 6, 4, and 9. So this is an example of an eclipse attack, which restricts an honest user's view of the network. These Byzantine nodes may then simply drop your P2P application request or respond with incorrect messages. Brunster et al. Conduct an eclipse attack against IPFS, where malicious users manipulate an honest user's routing table such that the user can only reach other malicious nodes and cannot obtain a correct copy of their desired content. So eclipse attacks pose a threat to DHTs and need to be prevented through an efficient scheme. One can imagine a majority filtering-based rule in order to drop invalid routing responses from Byzantine nodes. To do this more efficiently, we look at Young et al.'s robust communication protocols. So these protocols use threshold cryptography to provide integrity over routing table entries and prevent this attack. At a very high level, integrity is provided using a special type of digital signatures, that is, threshold signatures. There are 2 key differences in the routing table entries in RCP to what we just saw. So first, each node maintains a public verification key, VK, for each quorum in its routing table. For example, quorum 1 maintains verification keys for quorums 3, 7, 10, and 12 here. Second, each node also maintains threshold signatures over each element of the routing table entry. So that's the node network addresses and the public encryption keys, as well as the quorum verification key. So this is shown by the square brackets around the routing table entry with the subscript of the signing quorum. So that's quorum 1 here for node P. A node that knows any quorum's public verification key can verify a threshold signature from that quorum. So quorum 1's nodes can verify messages signed by quorums 3, 7, 10, or 12. Essentially, as long as there are enough good nodes in each quorum, we can use threshold signatures to propagate verified routing entries. In the first step of the robust communication protocol, node P requests for the routing entry for quorum 6, as usual in the RCP request message here. In step 2, it obtains the routing entry as well as a threshold signature over this entry. So this would be a threshold signature by the intermediate quorum, which is quorum 7 here. In step 3, node P can verify the routing entries for quorum 6's nodes using quorum 7's verification key from its own routing table. So the earlier attack does not work given Byzantine nodes such as node R and quorum 7 cannot convince enough honest nodes in its own quorum to construct a valid threshold signature over fake routing entries. Also, node P can now communicate with the target quorum through application level messages such as DHTPIR messages in steps 4 and 5 here. In step 5, node P gets assigned application response from quorum 6. Node P can verify this response using quorum 6's verification key as shown in step 6 here. So all that you need to know for your IPFS application messages is that you can now verify the responses from a target quorum using its public verification key that we obtained during routing. These RCP protocols provide integrity of routing responses. They do not provide confidentiality over routing query content. For example, in step 1, all nodes in quorum 7 know that node P wants to communicate with quorum 6. Backus et al.'s query privacy protocols hide which target quorum was looked up from all intermediate nodes in path to the target quorum. So there are two crucial differences between QP and RCP. First, the QP request to an intermediate quorum does not reveal the target quorum that's being looked up, so that's quorum 6 here. Second, for the QP response, each intermediate quorum, such as quorum 7, encrypts its entire routing table following an oblivious transfer or OT protocol. So in step 2 here, the ciphertext table is encrypted again for transit to the client node. The special thing about the OT protocol is that the client can only decrypt a single quorum routing entry of its choice from this innermost encrypted routing table. Again, it can verify the signature on that routing entry that it chose using the verification key for quorum 7. Keep in mind that none of the nodes in quorum 7 know which quorum's routing entry the client ended up decrypting. So the next steps that a P2P application takes to communicate with the target quorum, that's steps 4, 5, and 6 here, remain the same as in the RCP case. Since we build on top of Backus et al., the client reaches the target quorum 6 following the QP protocol, so steps 1, 2, and 3 remain the same here. This is when both of our protocols come into play. So we perform steps 4, 5, and 6 here with DHTPIR, application requests, and responses. So I'll now present the design of our private file retrieval protocol. So for our private file retrieval protocol, each quorum shares the same PIR database. Each database entry corresponds to a file, and the database is indexed by file identifiers. The client wants to find a file with a given identifier. In order to conduct IT-PIR, the client node P works with index vectors, as I mentioned earlier. The index vector is a unit vector with the 1 at the index of the block that is being retrieved from the database. So the client node P needs to be able to first map the file identifier to an index in the database from the target quorum. And to do so, we use a perfect hash function, or a PHF. And here we can see the steps of our private file retrieval protocol at a glance. First, the client node requests the target quorum for its PHF and then receives a PHF in response. It then uses this PHF to construct PIR request vectors. It sends PIR request vectors to the target quorum and receives PIR response vectors, which it uses to reconstruct the file. The client picks a node at random from the target quorum, and we refer to this node as a delegate node. Suppose the client chose the Byzantine node B. The client encrypts a PHF request to the delegate node, which then decrypts the message. Now I've said that each quorum maintains a PHF. To guarantee freshness, PHFs are associated with logical timestamps that increase with every new insert into the shared database. So a node in a quorum can quickly compute a PHF for the shared database. So in the PHF response step, the delegate node responds back with the PHF timestamp pair. To assure node P of the integrity of the PHF, the delegate node also returns a threshold signature over this pair. Node P can now confirm the integrity of the PHF by verifying the signature over it using Quorum 6's public verification key, which it obtained during the QP protocol. The RCP threshold needs to be calibrated carefully for the PHF response verification. This is because lazy Byzantine nodes should not prevent an honest delegate node from responding with a valid PHF, and at the same time, Byzantine nodes should not be able to collude to generate a valid threshold signature over a fake PHF, which excludes sensitive files. Okay, so now the client gets a valid fresh PHF, and it looks up the file hash in the PHF and obtains the index of the file in the database. We now follow a usual IT-PIR protocol. The client constructs a unit PIR request vector that would retrieve the file at that index non-privately, and it then generates one random PIR request vector for each node in the target quorum, such that when these vectors are combined, we get back the non-private request vector, as we discussed earlier. The client then encrypts a PIR request vector to each node in the target quorum using the node's public encryption keys. So in the next step, each node in the target quorum takes its PIR request vector and the shared database file and computes PIR responses. Each node returns a PIR response, again encrypted back to the client node P. The client then reconstructs the desired file using these responses. Again, Byzantine server nodes in the target quorum may mess with the privacy and availability guarantees for this step. So the Byzantine nodes here, nodes B and M, for example, may collude and share their PIR responses in an attempt to determine which item the client retrieved. And second, these nodes may send incorrect responses or just simply drop file retrieval requests. So Byzantine-robust IT-PIR schemes prevent these attacks, though we do need to parameterize the threshold for these IT-PIR schemes to work correctly. We have two constraints. We need to ensure that the IT-PIR threshold is high enough that these bad nodes cannot successfully reconstruct a PIR response by colluding amongst each other. To prevent the availability attack, the IT-PIR threshold should be low enough such that using only the PIR responses from the honest nodes, the client should be able to reconstruct the desired file. And so that concludes our file retrieval protocol. So let's talk about our file insertion protocol. We worked with the DHT storage model where any node only stores blocks whose identifiers are related to its node ID. In IPFS, nodes can store any blocks and simply propagate advertisements to other nodes. Our file insertion protocol can also be extended to IPFS with provider advertisements. The file needs to be shared across all nodes in the quorum for the private file retrieval algorithm to work. The client node P here could send the file to each of the S nodes in the target quorum. However, this is expensive, and instead, the client node delegates a random node from the target quorum with the task of sharing the file with its peer nodes. The client node P encrypts the file to that node. Now, perhaps node P ended up contacting our Byzantine node B, which might just drop the file silently without letting any of its honest peers know. It could also corrupt the file before passing it along to honest nodes. And so the client should be assured that the file was shared with a threshold of enough honest nodes. And so for this reason, we require the delegate node to respond back to the client node with a threshold signature over the hash of the file, much like we did with the PHF. Right, so the delegate node is responsible for forwarding the file and the insertion request itself to other nodes and constructing the threshold signature from each node and then forwarding it to the client. So with that, I conclude my description of our protocols, and I'll go into a summary of our security analysis. So as I've discussed, while designing our file insertion and retrieval protocols, we consider attacks by Byzantine server nodes. In our paper, we also consider Byzantine client nodes and include protections against them in both of our algorithms. For our protections to work, we express constraints on the RCP threshold and IT-PIR threshold in terms of the fraction of Byzantine nodes per quorum. We arrive at the maximum number of Byzantine nodes per quorum, as well as across a network that our scheme can withstand. And we find that quorums in DHTPIR can tolerate less than a quarter of their nodes being Byzantine. So, what is the corresponding global fraction of Byzantine nodes across the network? To answer this question, we simulated the Commensal Cuckoo rule while ensuring that each quorum always had less than a quarter of Byzantine nodes. This local bound of a quarter translates to a global bound of at most 2% of the network. In other words, at most 1 in 50 nodes in the network could be Byzantine nodes. We've simulated large networks of about 10 million nodes and maintained quorums of an average of 20 nodes and at most 75 nodes. So what about the efficiency of our system for these network and quorum sizes? So we have simulated our system and compared it to the best related work as well as baselines. In this talk, I'll focus on the DHTPIR simulation in contrast with the baseline of a hardened DHT, that is the RCP and the QP protocols as applied to routing entries over quorums, but no privacy over file retrieval queries. We've assessed the scalability of our system as more blocks are stored across the DHT, as well as with increasing numbers of peers and larger quorums. For this talk, I'll focus on scalability as more blocks are stored in the DHT. We simulate one node inserting many files into each system and then retrieving them. We focus on the performance of our private file retrieval algorithm. So we plot the total communication complexity for our simulated systems as the number of files per quorum increases. The total complexity includes the size of all messages in both the file retrieval requests and responses. We note the log scale on both axes. In the DHTPIR simulation for our chosen Byzantine-robust IT-PIR scheme, the PIR requests and responses are the size of the square root of the database. The client communicates with all of the S nodes in the target quorum twice, once for each PIR request and once for the PIR response. So we have a total communication complexity of 2S times the square root of D. Given that the quorum size is kept constant, we can see that the DHTPIR total communication complexity, which here is shown in the red dashed lines, scales with the square root of the number of files per quorum as expected. We also plot the throughput as the number of files per quorum increases. By throughput, I mean the number of simultaneous client's file retrieval requests that can be handled by the simulated systems. DHTPIR performs the same regardless of the number of cores until quorums have around 2,000 chunks each. Until this point, DHTPIR is network limited. After this point, adding more cores to nodes results in an improvement in the throughput. Our simulation demonstrates the potential efficiency of a DHTPIR implementation. With that, I'll briefly talk about our proposal submission towards the Protocol Labs RFP on private retrieval of data. Our goal is to produce an IPFS integrated design for DHTPIR and its underlying protocols. Towards this goal, we'll first need to analyze the compatibility, interoperability of our protocols with the IPFS model and architecture. We may need to revise some protocols and parameterize them. I'll talk more about these compatibility questions soon. Towards our second goal, we'll first associate relevant IPFS libraries that will need to be changed. We will then develop a private or secure interface over the respective IPFS libraries for that protocol. Finally, we will implement and test our interfaces using the IPFS test ground infrastructure. So let's start with the questions for the PIR layer of our work. We've talked about CPIR and IT-PIR. Our IT-PIR scheme requires a quorum of nodes to share a common database. Is this a feasible model for IPFS nodes? I'll talk a bit more about forming quorums in IPFS soon. We also want to compare the latency as well as communication and computation overheads for the CPIR or IT-PIR schemes that we're considering. Given that IPFS aims to deliver low latency lookups, we want to select the scheme with the lowest latency and moderate communication overhead. We will also parameterize constants for the PIR scheme we choose, such as the IT-PIR threshold. Finally, we will develop a PIR interface that extends the relevant IPFS libraries, such as the bitswap protocol, for a client node to fetch a block from one or more server nodes privately. We will also implement and test this interface in comparison to the non-private version. So we formed quorums using the Commensal Cuckoo rule, and we conducted routing with integrity and confidentiality guarantees through the RCP and QP protocols respectively. As Kademlia has been proposed to secure the underlying Kademlia DHT used in IPFS, and work is in progress to integrate Kademlia into the P2P. So our goal here is to assess how we can use and adapt Kademlia to build trustworthy quorums for robust routing as well as for IT-PIR. Kademlia proposes sibling lists with an availability guarantee on being able to contact enough sibling nodes in this list. We use the Commensal Cuckoo rule to form quorums. So an interoperability question is, can Kademlia's sibling lists be used to form threshold on quorums as in CCR? Kademlia does not require coordination between existing nodes as a new node joins the DHT, whereas CCR does. So we may want to compare the communication overhead for a new node joining the DHT, including sharing database state under CCR and under Kademlia. And in terms of robust routing, Kademlia includes a multiple disjoint path algorithm to deter Eclipse attacks. In contrast, RCP provides a somewhat stronger guarantee of preventing Eclipse attacks. So we may wish to strengthen Kademlia by integrating RCP. And we will assess whether Kademlia's multiple disjoint path algorithm can be replaced with RCP. We would answer questions such as what communication overhead would Kademlia with RCP incur for conducting a routing query, and compare this overhead to Kademlia with the multiple disjoint path algorithm and Kademlia itself. And so with that, I've summarized the kind of questions and challenges that we outlined in our proposal. So to summarize, we provide plausible deniability over queried content for DHTs by integrating private information retrieval, or PIR, into hardened DHTs. Our architecture allows a user to privately retrieve a document from the network without the nodes in the target quorum or any in-path nodes learning what document was retrieved. We conduct a security analysis and a simulation for our system's performance. We have submitted a proposal to integrate DHTPIR into IPFS and have described some relevant challenges in this talk. Our paper, including an extended version as well as code for our simulations, is available on this link. Thank you for listening, and I look forward to your questions.